Hey everybody, how y'all doing? I just recently got home here from recording lectures 21A and 21B, and I've got a few things to say here before lecture 21A starts. First, I just want to give a shout out and thanks to all my Bethel students and all my viewers and subscribers out there. I really appreciate that you watch. And I'd like to also just ask if you really like the content of lectures 21A and 21B to make sure you like and subscribe. I really put my heart and soul into it, and I really am pretty satisfied with the results. Second, I just want to also emphasize that making lectures 21A and 21B was really a pure joy for me. The content is really interesting, I think. It's quite challenging, especially the first half of lecture 21A. And if your goal is to get to the content of the second half of lecture 21A, I will put a timestamp to that content to help you get there. But I do feel like the content is really beautiful, and I hope that comes across clearly. This content is really the culmination of everything that we've done in the course so far. And I personally think it's super beautiful how the ideas, the symbols, and the graphs all come together in a nice synthesis. In fact, I praise God that He has given us the minds to be able to understand this aspect of His creation. In fact, I feel like Eric Liddell from the 1981 Oscar-winning Best Picture movie called Chariots of Fire, who said to his sister, "God made me fast, and when I run, I feel His pleasure." Well, I want to say, God made me enjoy math, and when I do math and I explain it to you, I feel His pleasure. God also helped me be able to do my very best in these lectures, especially since I caught a cold about 10 days ago, and I was actually sick enough last weekend that I decided to get a COVID test. Praise God, I found out yesterday that it came out negative. I don't have COVID. But let's keep in mind that there's lots of people suffering in our world because of COVID and other aspects of what's going on. Make sure you take the time to reach out to family, friends, acquaintances, and even strangers to help in whatever ways you can help them through this time. And now, without further ado, here's lecture 21A. Lecture 21A of Differential Equations and Linear Algebra will be split into two main parts that will seem unrelated to each other at first, but we will ultimately see in later lectures that they are related. The first part is kind of a heavy-duty theory section. We're going to use the Uniqueness Theorem for autonomous ODEs to prove the group property of a flow for those autonomous ODEs. This is a big part of continuous dynamical systems. The second part of the lecture, we're going to get more concrete with an example. We're going to introduce the idea of eigenvalues and eigenvectors by looking at a linear system and looking for what are called straight line solutions. In lecture 21B, we do the linear algebra portion. We look at rank theorem applications, but we also look at a system of linear difference equations. And we also look for what are effectively straight line solutions, orbits that are on straight lines in that case. That's discrete dynamical systems. All right, so let's start by reviewing the unique existence and uniqueness theorem for differential equations. This is not the only way it can be stated. I'm trying to state it in the simplest way possible for us. Let f of t comma y be a continuous and ultimately continuously differentiable vector field. It is possibly time dependent. We are allowing for that, though when we look at autonomous systems, those are not time dependent. Those are time independent. So it's a vector field, possibly time dependent. We are assuming it's continuously differentiable everywhere and in all variables, meaning all the partial derivatives of all the components exist and are continuous everywhere. That's something that makes this a little extra special here, makes it as simple as possible for us. We can restrict those assumptions somewhat, but this is going to be good enough for us to get to the main point of what we're trying to do. The conclusion is there exists a unique solution to the following initial value problem on some possibly very small interval containing the initial time, t0, which is often taken to be 0. There's our initial value problem. dy dt equals f of t comma y, and y of t0 equals y0. There's your first order system of differential equations in vector form, and there's your initial condition. There is a unique solution to this once the vector field here is nice enough, continuously differentiable, say, everywhere and in all variables. What does that mean? That means there exists a unique function that I'm calling capital phi sub y0 of t. In your mind, you want to think of y0 as fixed and t as the variable. So this describes a parametric curve in space, in Rn in fact. I'm not restricting myself to 2 dimensions, for example. I'm in an arbitrary number of dimensions. That's defined for all t in some interval of this form. Some possibly very small interval from t0 minus epsilon to t0 plus epsilon. That satisfies the differential equation and the initial condition. What does it mean to satisfy this differential equation? It means when you plug it into the left-hand side and the right-hand side and simplify, you get the same thing. In the abstract, that means when you take the derivative of this function with respect to t, find phi prime of t, you get the same thing for all t as when you replace boldface y in the vector field with that function phi of t. Okay, that's going to be true for all t in some possibly very small interval. The size of the interval could depend on t0, it could depend on y0, it certainly depends on the vector field itself. And it satisfies the initial condition. When you plug in t0, you get the initial point y0. All right? Now we're going to make even more assumptions. We're going to get rid of the time dependence. We're going to assume we've got an autonomous system, time independent, just an f of y there, no t at all. And we're also going to assume, for the sake of simplicity, okay, this is not always true, but just for the sake of simplicity, that, well, first of all, t0 is taken to be time 0, which is the most common thing to do anyway, but more importantly, that for all y0, the unique solution exists for all real numbers t. Epsilon effectively is like it's infinity, okay? Or you might say there is no epsilon. This is true for all t, for all real numbers t. That's a very not common thing with nonlinear systems. Usually with nonlinear systems, the solutions are not defined for all time. Oftentimes they go off to infinity in finite amount of time, either as t increases or as t decreases. So this is a very restrictive assumption. What do you do if you are in a situation where this doesn't happen? It turns out you can modify the system to make it happen. The new system is not the same as the old, though the behavior of solutions is the same. I'm not going to get into those details. Then, for any fixed time, as we talked about a few lectures ago, we can define the time t flow map using this notation. This is my notation. This notation is not absolutely standard, but I think it's the best notation. What do I have here? Okay, this is a little confusing. What am I doing? That's your solution for fixed y0 as a function of t. You're thinking of y0 as fixed, you're thinking of t as a variable. This describes a parametric curve in Rn, in space. I'm defining this other, that's a fancy phi superscript t of y0 to equal the same thing. But my perspective has changed. Now I'm thinking of t as fixed, and y0, the initial condition, as the variable. Weird. But yes, that's what we want to do. Maybe we shouldn't call it y0 then, but well, we'll remind ourselves that it's still the initial condition. But it's now the variable. Can I do this? Sure, you always can change your perspective on what's the variable and what's a constant. Okay? That's always something you can do. The real issue is it beneficial? And we will see ultimately that it is beneficial. Okay? So when I think of, here I'm thinking of this function as a function from taking real number inputs and giving you point outputs in Rn. Here I'm thinking of this as being a function that takes point inputs or vector inputs and gives you point outputs. Also, it's just a change in perspective. The flow itself is considered to be the family of all such mappings here, phi t, as t varies over all real numbers. And that's why I want to have this extra simplicity assumption that I'm making up there. Okay? It's a family of functions. We'll see that when the system is linear, this family of functions is a family of linear transformations. But when the system is nonlinear, it's not a family of linear transformations. But it's still something that is worthwhile to think about. Our goal is to use the uniqueness theorem, or the uniqueness part of the existence of uniqueness theorem, to verify the group property of the flow, what I also call the flow property, for short. This property right here. That when you compose these, the time t map with the time s map, you get the time t plus s map for all real numbers s and t. When this simplicity assumption is not met, this can still hold, but for more limited values of s and t. That's what we want to show. This group property is related to group theory. I'm going to briefly talk about that in the next lecture, if that's of interest to you. But it's real important for us, and it only holds for autonomous systems. We saw in a previous lecture that it did not work for some non-autonomous examples, even though I could still make this definition. And it's the key to connecting differential equations with difference equations. That's what we're really after here, as well as some other things. All right, wait, but why do we do this? What's the purpose? Recall that the group property of the flow, again, also known as the flow property, for an autonomous system, allows us to relate what I just said, the differential equation, to a difference equation. The differential equation to a difference equation. How? To be precise, the solution y sub n of the difference equation, this one right there, y sub n is the time 1 map. Here I'm picking a particular value of time 1, that's the most common thing to pick because it's sort of the simplest thing to think about. Apply to yn minus 1, that's a difference equation that I can iterate to generate a sequence of points through space with the same initial condition as the ordinary differential equation, y0, has the property that, this is true right over here, y sub n, the solution of the difference equation, equals capital Phi sub y0 of n. That's the solution of the differential equation at time n. They're equal to each other. That's actually a pretty significant thing, because what it means is studying one might help you understand the other. And usually what we do is we use the difference equation, this thing and its solution, to help us understand the differential equation. Usually it goes that way, but theoretically it could go back and forth. We could maybe understand the difference equation by looking at the differential equation. There are other benefits too that we're going to see. It's going to help us make some nice definitions later on that will help us understand things with differential equations better. That's other benefits to come when we get to chapter 5 in Blanchard, Devaney, and Hall. But why does this happen? Why does this equation right here happen for an autonomous system? It doesn't happen for non-autonomous when we look at this difference equation and its solution. It's because of the group property of the flow. Here are the details. Okay? Think carefully here. Yn, what does it equal? Well, it equals that. There we go, right? But this is a difference equation, a recursive equation. I could iterate it. I could keep using it over and over again. I'm generating a sequence. Yn is phi1 of yn minus 1, but yn minus 1 is phi1 of yn minus 2. Like that. And yn minus 2 is phi1 of yn minus 3, etc. We can relate it all the way back to our starting point, our initial condition, y0. Phi1 of phi1 of phi1 of dot 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 of phi1 of y0. How many phi1s are there? I guess the pattern is the number of phi1s is going to be the same as the number you subtract there from n. 0 is n minus n, so there must be n phi1s there. And the group property of the flow, GP prop means group property of the flow, says that I can combine this into one flow map by adding those numbers. It's as if they're exponents. Are they really exponents? Not in the usual sense, because phi is not a number, but they sort of act like exponents. I can add them. I get this. But wait a minute. By definition, that's this. That was the definition of this curvy phi function. Superscript, say, I had t before, but now I have n. It was defined in terms of the solution of the ordinary differential equation, the autonomous ordinary differential equation. There's nothing to show there. That's a definition. And there we have it. That verifies this fact right here. The group property is necessary right there. It's also worth noting a couple other things here. Well, one main thing, that if you plug in t equals 0 into the flow map, time 0 flow map, the group property of the flow says phi 0 composed with itself would be phi 0 plus 0, but hey, 0 plus 0 is phi 0. Interesting. Phi 0 composed with itself, the time 0 map composed with itself is the time 0 map. What does that mean about the time 0 map? I guess it would mean it has to be the identity mapping. Which is a linear transformation, actually. It maps every vector x in Rn to itself. Its matrix would be the identity matrix. I guess that would have to be the case. Maybe you want to see if you can figure out why this would imply that. It does. That could also be verified another way. Excuse me. You could plug in time 0 into here, related to the solution at time 0, which is y0, and that's true for all y0. Okay, it doesn't matter what y0 is, and because of that, phi 0 maps an arbitrary vector to itself, an arbitrary point in Rn to itself, therefore phi 0 is indeed the identity mapping on Rn. That's also useful to realize sometimes, okay? But why is the flow or group property true? Why is it true? Okay, this is the hardest slide. You ready? Get all psyched up, ready to go, really, really focus like a laser beam. Pay attention here. This is a little bit tricky. Let y0 be a fixed point or vector, if you prefer thinking of it that way, as in Rn, and let s be a fixed real number. It's important that these are fixed. Okay, so in your mind, you're imagining these to be fixed. Furthermore, for the sake of simplified notation, I'm going to let y sub s, for this fixed number s, be phi s of y0, which does equal this because curvy phi is related to the capital Phi in this way. That's the definition of the cursive phi. Fancy phi. It's its definition. I'm going to draw a little picture here to help us think this through. So, generic picture, I'm drawing it on the board as if it's R2, but you want to imagine it's R3 or maybe R million, million dimensional space if you want. You've got your point right there, your initial condition. S is a certain fixed amount of time. We can pretend it's positive. Ys is the value of the solution. Focus on this one. It's the value of the solution to the differential equation with initial condition y0 at time 0 at time x. So it's like you follow the solution curve forward in time by s units of time, and you get to this point ys. So s units of time have elapsed, you might say. Okay, you're at this new point. All right, that's not too bad. What's next? I'm going to define two functions, boldface g and boldface h. They're going to be defined for any real number t by the following formula. So I'm going to show you a couple formulas. In these formulas, you want to imagine, you know what's fixed, y0s, and in fact ys is fixed as well. And you want to think of t as the variable. Okay? Though because you can do this for any t, you could think of t as a constant as well, but think of t as the variable. That's probably the best way to think about it. G of t is defined to be cursive phi s plus t of y0, which by definition is the same thing as this, capital Phi sub y0 at s plus t. And let h of t be phi sub t, not of y0, but of ys, which by definition would be not phi sub y0, but phi sub ys of t. What's going on here? Focus on h, that's easier to understand here. H is, it is in a sense just this, okay? I could have just called it that. It's the solution of the differential equation, the autonomous differential equation, with initial condition ys at time 0, followed forward in time by t units of time. So that's like starting at ys at time 0 and following it forward t units of time to get to a new point up here, which is going to be h of t. It's going to be phi sub ys of t. So t units of time pass there. If I imagine t to be fixed, a fixed positive number, t units of time elapsed, starting from time 0. What's g of t? G of t, focus on this part, takes the solution with initial condition y0 at time 0 and follows it forward s plus t units of time. Starting here at y0 and following at time 0 and following it forward s plus t units of time. You would think you'd have to get to the same spot, right? You would think this would have to equal g of t. And that is true because the system is autonomous. If it's not autonomous, what could happen is you could be focused on the solution starting at y0 at time 0 and following it forward in time to this spot when time is s. But at time s, because the vector field for a non-autonomous system is time dependent, the vector field could be pointing in a different direction when t equals s. And that solution could head off that way and not head up here once we get to time s plus t. But for autonomous systems, the vector field is time independent. It doesn't vary over time. It will continue following the same path as if you start here at time 0. That's the big idea. G of t will equal h of t, and I claim that verifies the flow property. Claim two things. Number one, what I just said, g of t equals h of t for all t. And number two, claim one, this one, verifies the group property, or flow property. Initially I called it a flow property and said I also call it group. I'm more focused on calling it a group property now and saying I also call it a flow property sometimes. But why is one true? The proof of claim one follows from uniqueness and a couple calculations that are a bit confusing, but you can do it if you keep your wits about you. I'm going to first verify G satisfies the differential equation, and also that at time 0 it satisfies the initial condition where it equals ys. And I'm going to verify the same thing for h. And by uniqueness, that will mean g of t has to equal h of t. Here are the details. G prime of t, that's a derivative with respect to t, so I can write d dt. This thing right there is just the definition of what g is. G is that, so that's what I'm using there. I'm just substituting. But how do you take the derivative of this? Well, it's a minor application of the chain rule. This is a composition of two functions. Think of s as fixed. It's the function s plus t as a function of t. S is fixed as the inside function, and capital Phi being the outside function. So I take the derivative of the outside, plug in the inside, and multiply times the derivative of the inside. That's the chain rule right there. Let's use green here. That's the chain rule. It's a trivial application of the chain rule because the derivative of s plus t with respect to t is just 1. Oops. But it's fortunate that that happens because it helps you finish the problem. Multiplying by 1 doesn't change it. I just have this derivative. But wait a minute. Capital Phi solves the autonomous differential equation. I can replace capital Y in the autonomous right-hand side, plug it into the vector field and get this. But wait, that's the same as g of t. Okay, so this means g of t satisfies the differential equation. G prime, the left-hand side, equals f of g of t, the right-hand side, for all t evidently, and then g of 0 does equal, plug in t equals 0 up here, and you get this, which does equal ys by the definition of ys. H of t satisfies the exact same initial value problem. H prime is the derivative of this because that's the definition of h. Now take the derivative of that, get this. But hey, that's a solution of the differential equation. Left-hand side equals right-hand side. When I plug it in the vector field, I get the same thing for all t. These are true for all t, by the way. And that's h of t again. So yes, h prime equals f of h of t. For all t, it satisfies the differential equation. Furthermore, h of 0 does equal the same point ys. So G and H both satisfy the same autonomous initial value problem and since we're assuming F is a nice vector field, by uniqueness I can say G of t must equal H of t. These are the exact same functions. You might wonder, where does it go wrong if you assume the differential equations are non-autonomous here? If it were non-autonomous, the place it goes wrong is you'd have to have, in this spot here, you'd have to have an extra s plus t comma in front of this. But down here you'd have to have an extra t comma, and these would not be the same ultimately. Okay? So the non-autonomous would get messed up at that spot if your system was non-autonomous. What about claim 2? Claim 2 says this means we're done, essentially, is what it means. Claim 2 follows because G of t equaling H of t for all t means that, well, each step here, phi t plus s of y0 is phi s plus t of y0. Why did I do that? Just because it's based on how I phrased the flow property before. I wrote it as phi t composed phi s equals phi t plus s. So I'm starting with the right-hand side there, t plus s instead of s plus t. I did that just because it makes it work out nicest. And here I'm just noting t plus s does equal s plus t, so that's not a big deal. Okay, what's next? Relate that to what? To the fact that h of t equals g of t. That's what I'm using right here. G of t equals h of t. That's what's being used. This equals that. That's claim 1. I'm using it now. Okay, well, what's ys? It's that. This is ys. Right? Compare with this. Ys equals that. And then, hey, that's the same thing as phi t composed phi s of y0. And y0 is arbitrary. So that's true for all y0 and Rn. And s is arbitrary. The final result that this is true follows because s and y0 are arbitrary. Even though s and y0 were fixed, in my thinking, they're arbitrary. So the argument works no matter what they offer. So this has got to be true no matter what s is. The flow property works. All right, heavy-duty theory. Now we're on to some more concrete example here. Straight line solutions of a linear system. I'm really excited about lectures 21a and 21b here because it's the culmination of so much of what we've done to this point. And they're going to be very much related to each other, lectures 21a and 21b from this point on here. Straight line solutions. This is an introduction to eigenvalues and eigenvectors. A lot of calculations here. I do want to show you a picture as well at the very end. Consider the first order system. So we have an example here. I picked a matrix. Capital A is this matrix whose entries are 1, 3, 2, and 2. This is a linear system of differential equations. Okay? Nice system. Definitely existence and uniqueness hold, that kind of thing. But moreover, we can find formulas for solutions, or at least that's what we hope. Let's hand sketch the null lines and the phase plane as quick as we can here. The x null line is where dx dt is 0. That's going to be based on x plus 3y equaling 0, which is equivalent to y equals negative 1/3 x, a line with the slope of negative 1/3 through the origin. And the y null line, we've talked about null lines a lot, is where dy dt is 0. That's where 2x plus 2y is 0, which is equivalent to y equals negative x, a line with the slope of negative 1 through the origin. So let's quickly try to sketch the null lines and the phase plane, try to draw in some plausible solution curves. The x null line Goes to the origin with a slope of negative 1/3, maybe about like this, say. And that's an x nocline. dx dt is 0 there. Solutions have to cross that vertically with vertical tangents. This is the x-axis, this is the y-axis. The y nocline, y equals negative x, looks about like this. Not perfect. Solutions have to cross that horizontally because dy dt equals 0 there. Where x and y noclines intersect, where red and blue intersect, we have an equilibrium point, a unique equilibrium point at the origin. Make sure you draw that. That's very important. What about other solutions? You can think about the sign of dx dt and dy dt to help you figure out directions for solution curves. For example, dx dt is positive where this is positive and negative where it's negative. It's 0 along this line. It's got to be positive above it. If you try just plugging in some points, you'll see x plus 3y has to be positive when you're above it. dx dt has to be positive when you're above the red line and negative when you're below it. So it's going to be rightward motion of solution curves above the red line and leftward motion of solution curves below it. dy dt is 2x plus 2y. That's positive above the blue line and negative below it. dy dt is positive above the blue line, here and here, and negative below it, down here and here. So solution curves in this region go to the northeast. Solution curves in this wedge here go to the northwest. Solution curves down here go to the southwest. And solution curves in this wedge go to the southeast. Your solution curves, if you draw a quick sketch, you realize they have to do something about like this. And you can never sketch these things perfectly, but do your best job and certainly try to cross those noclines correctly. It would seem reasonable, I hope, to say, you got this divergent behavior based on the initial conditions, very subtly. It seems like maybe there should be a solution that heads maybe straight toward the origin in here. And also in here. I didn't draw it very well. I didn't draw this very well. These should not intersect because of uniqueness. So if I were going to do it again, I'd try to draw it better. And maybe also solution curves going away from the origin here and here. Also not drawn very well. You might wonder, are these the same line in both cases? They are. I did not draw this one to look like it's the same line because my drawing is bad. Okay? We will work on getting better drawings. And are those straight lines really? Are those straight line solutions? Parametric curves that are straight? Based on this, we wonder, does the system have any straight line solutions? Of what kind of form would that be? Some scalar valued function, call it f of t, or maybe I should have used a different letter, h of t, times v. Could there be some solution that would look like that? Since v is a constant vector, if you graph this as a parametric curve, it's going to be along a straight line, through the origin, in fact. Moreover, based on our experience with differential equations and how their solutions often involve exponential functions, we might wonder whether f or h of t has a certain form. E to the lambda times t, where lambda is constant. And we'd be right if we hypothesized such a thing as we're about to see now. Let's just see if any choice of the number lambda and the non-zero vector v will work. V does have to be non-zero, because if it were 0, then you'd just be at the origin. Although, I mean, v equals 0 does work, but that's just the equilibrium point at the origin. We know about that already, so we don't really need to do any work for that. So try it and just see what happens. Sometimes you just got to do that. Try something and see what happens. You may be lucky and things work out. Maybe you're unlucky and things don't work out. I mean, you do gain skill at guessing over time when you work with these things enough. What happens if we guess this? I'm just writing it this way as well, to say V has some unknown components x and y. Well, what would the left-hand side of the differential equation equal? It would be y prime, which because of the chain rule would give you an extra factor of lambda here. That's the chain rule. And that would simplify to this if we wrote it in terms of its components. I also could take the scalar and put it in the components. I could do that. I could multiply the scalar times the vector. I'm not, but I could. What about the right-hand side? A times y. Replace y with what it equals. You can, it turns out, factor out this scalar out in front like that. And we could plug in the matrix A if we wanted as well. If this is going to be a solution, these two things in red and blue must equal each other for all t. Focus first on these parts. I want those to equal each other no matter what t is. I guess I could cancel the e to the lambda t's, couldn't I? E to the lambda t is never 0. It's a scalar. I could divide both sides by it, or multiply. Think of it as multiplying both sides by e to the negative lambda t. So I can make that go away. And I guess that would mean lambda times v, the scalar lambda times the vector v, which is a vector, would have to equal the matrix A times the vector v, which is also a vector. Yeah, that's what we want. These will be equal if and only if the matrix A times the vector v equals the scalar lambda times the vector v. Both sides of that equation ultimately are vectors. A matrix, 2 by 2 matrix times a 2 by 1 vector is a 2 by 1 vector. A scalar lambda times a 2 by 1 vector is a 2 by 1 vector. This does not mean A equals lambda. A cannot equal lambda. A is a matrix, 2 by 2, lambda is a number. They're not equal. Don't think that that means A equals lambda. It doesn't, though A and lambda are related. In terms of components, you could write it this way, plugging in the matrix. After multiplying this matrix times that vector, you could write it that way. We'd want these two vectors to be equal. Certainly they're equal if x and y are 0, but we're wondering, are there non-zero solutions for x and y? Or at least where one of them is non-zero. These are equivalent to these equations. I could go from here to here by subtracting lambda times v from both sides to get this equation. But then I could also sort of go backwards here and factor out of v. I could think of lambda times v as lambda times I times v, where I is the 2 by 2 identity matrix. And then I could factor a v out of that and get an a minus lambda times I. This 2 by 2 matrix minus the scalar lambda times this 2 by 2 matrix, the identity matrix I. I'm wondering, are there non-zero solutions for v where this matrix times v is the 0 vector? V would have to be in the null space of that matrix. The kernel of the corresponding linear transformation. Hey, null spaces and kernels. Linear algebra. Yeah, all those concepts that we've talked about. In terms of components, this is the matrix A minus lambda I here. Think about it. I is 1, 0, 0, 1, so lambda I is lambda 0, 0, lambda. I subtract, it means I subtract entry by entry. It's the upper left and lower right entries that are going to get us lambda subtracted from them. The main diagonal there. The off diagonal entries get 0 subtracted from them, so they stay as they are. And then I could multiply the matrix times the vector. I could write it this way, and this is a system of linear equations. And as we talked about with determinants and the invertible matrix theorem, for there to be non-zero, non-trivial solutions of this homogeneous system, we know by the invertible matrix theorem that the determinant would have to equal 0. Right? When it's non-zero, that's when it's invertible, and that's when there's only the trivial solution. That's equivalent to being invertible. So therefore, the determinant equaling 0 would be equivalent to non-invertibility, which is what we want here. We want non-invertibility of this matrix because we're looking for non-zero solutions for x and y. Or for the vector v, I should say. Tracking with me here? So evidently this determinant must be an important thing to compute. Yeah, it's got a name. It's called the characteristic polynomial of the matrix A. It is a quadratic polynomial in lambda, and its roots are called the eigenvalues of A. This thing right here, that's the characteristic polynomial. Setting equal to 0 and solving for lambda gives us a quadratic equation in lambda. The roots of that are called the eigenvalues of A. Is it clear that it gives you a quadratic equation? Well, think about taking the determinant of this thing. Yeah, you multiply these things and subtract the product of those. It'd be a quadratic in lambda. You can use the quadratic formula, or if you're lucky, you can factor it. They're called the eigenvalues. In this example, here's the calculation, determinant of this. This is A minus lambda I. Multiply these two to get this. Subtract the product of 2 and 3 means subtract 6. Multiply that out with FOIL. First times first is 2. 2 minus 6 is negative 4. Outside side times outside is negative lambda. Inside times inside is negative 2 lambda. Combine those to get a negative 3 lambda. And last times last is negative lambda times negative lambda is positive lambda squared. And that, we are lucky, can be factored like this. So the roots of this characteristic polynomial are called the eigenvalues, and what are they? They're negative 1 and 4. The eigenvalues are negative 1 and 4. Those are the two numbers for this matrix such that this system has non-trivial solutions, and because of that, it's going to mean this function, when lambda is negative 1 and 4, both of those examples give you solutions as long as you pick the vector there correctly. V has to be picked correctly as well. Lambda is called an eigenvalue. V is called an eigenvector. What are the non-zero vector solutions called eigenvectors that correspond to these eigenvalues? In this example, plug the eigenvalues into C. Solve the system. If lambda is negative 1, plug it into the system. This again is A minus lambda I here, which if lambda is negative 1 is the same as A plus I ultimately, times the vector xy equals 0, 0. This is an augmented matrix here. 1 plus 1 is 2, 3 is 3, 2 is 2, 2 minus negative 1 is 3. Right-hand sides are 0. Do row operations. Hey, this matrix, the rows are the same. They're the same equation, essentially. They're equivalent to the same equation. This is you're going to get a row of zeros here. The general solution of the corresponding system, therefore, in parametric vector form could be written this way. Think of y as a free variable. Y equals itself. You've got a y times 1 down there. X would be, because this is the same as x plus 3 halves y equals 0, x would be negative 3 halves y, thus the negative 3 halves right there. What about for the other eigenvalue? Lambda is 4. So, by the way, all the non-zero vectors in this set are eigenvectors. As long as y is not 0, you get a non-zero vector here. It's an eigenvector for that eigenvalue. There's infinitely many eigenvectors, though you only have to use one of them. If lambda is 4, do the same kind of thing. This now becomes A minus 4i, ultimately, which simplifies to this augmented system that I can solve. The rows are not the same in this case, but they are multiples of each other. Once again, when we do row operations, we'll get a row of zeros. And this line says x minus y equals 0, or x equals y. If I think of y as a free variable, there's the parametric vector form of the solution set. As long as y is non-zero, I get a non-zero vector, and it would be an eigenvector for A corresponding to the eigenvalue 4. Eigenvalue and eigenvectors go together. They pair together. Any vector like this where y is non-zero is an eigenvector for that eigenvalue, not the other one. Any vector like this where y is non-zero is an eigenvector for this eigenvalue, not the other one. And no other vectors in the plane are eigenvectors for either of these. So now if we use the lambdas and the v's, the eigenvalues and the eigenvectors, you should take the time to check that these two functions both solve the differential equation. Excuse me while I take a drink. You should take the time to check that. okay? It's not hard. Do left-hand side equals right-hand side. You'll see it works. It's pretty cool to check it, in fact. Yay, we're happy that it works. What does this mean about the general solution? Now some theory comes into play. It turns out that the solution space of a two-dimensional linear system like this is going to be a two-dimensional vector space. Not proving that right now. That takes proof. But if we assume that's true, the basis theorem means that if we have a linearly independent set of vectors that are both solutions here, excuse me, they are linearly independent. They're not multiples of each other, which is all you need to think about with two vectors. The basis theorem is going to mean they automatically span the solution space as well, because the solution space will be two-dimensional. So any two linearly independent vectors will also span and therefore be a basis. And that means the general solution is an arbitrary linear combination of these, like this. That is the general solution. You can use it to solve any initial value problem that you want. And I'd encourage you to try an example. All right, let's end the lecture A here by looking at Mathematica quick. I've got the matrix A in here, and I've got the null lines in this animation as well. This is the, well, the orange and brown lines are the null lines. The red arrows are the vector field, essentially, just scaled down. The blue curves are solution curves. Notice how they cross the null lines. What are the green and the pink arrows? The green arrow is a position vector for any point that I want. And the pink arrow is the corresponding output of the vector field. And notice when I'm along a straight line solution, these are parallel to each other, like here, and down here, and in here, but with the opposite direction, and over here, when I'm on the straight line solutions. That eigenvalue eigenvector equation, A times V equals lambda times V, is saying I'm looking for non-zero vectors, V, where the output of the vector field, AV, is a scalar multiple of V itself, meaning it's parallel to it. When lambda is positive, it's in the same direction. When lambda is negative, it's in the opposite direction. Thanks for watching.